Hello, in this video we're going to be looking at another example of computing the Laplace transform of a function. The function in question will be f given by f of x is equal to t squared times e to the power, oh my bad, it should be x squared times e to the power minus 2x. So this is the function that we're given, and we want to find its Laplace transform. How do we do that? Well, in this case, there is nothing much to do except to apply the definition of Laplace transform. And let's remind ourselves that according to the definition, the Laplace transform of f is a function of s given by integral from 0 to infinity of e to the power minus sx f of x dx. So what we want now then is to substitute the expression for this fx over here into the integral. Doing that, we will get integral from 0 to infinity of e to the power minus sx times x squared times e to the power minus 2x dx. Some terms can be arranged, grouped together here. We have integral from 0 to infinity of x squared e to the power minus x goes out as a common factor, then we're left with 2 plus s dx. And then the big question, of course, is how to carry out this integration. So the first thing we want to do here is to remind ourselves what is infinite integral. Infinite integral, let's say from 0 to infinity, of some function, let's say g of x dx, is defined as the limit of the definite integrals from 0 to r, as r goes to infinity, of g of x dx. And that's exactly what we want here, where this general definition of infinite integral allows us to write this one as the limit as r goes to infinity of integral from 0 to r of x squared e to the power minus x 2 plus s. Okay, making a standard error here, writing the power in a big script so that later on I'll get confused it to be not in the power anymore. So that's what we want. And of course, we still need to integrate this thing from 0 to r, and for that we will use integration by parts. Okay, so that's going to be a long process, but since integration by parts is familiar to you, I'm going to pause the recording for now, do all the calculations, and then continue the recording and show you the calculations I got, and continue from there onwards. So this is what I got as the antiderivative of the given function. So I wanted, in order to compute this limit, first what I want to know is what the antiderivative of the function here is, of this function. So I carried out the calculation by using integration by parts. I treated this as integral of uv prime, which is equal to uv minus integral of u prime v. I'm not using definite integrals here because at the moment I'm only going to get the antiderivative. And so for getting an antiderivative, it is sufficient that I just pick one antiderivative. I don't need to introduce the constants when integrating. So by matching this with that, I take u to be x squared, and then I match the exponential function here with v prime, and that's how I get this result. And then I have to do this again because still this part needs to be integrated, and I do this again, and then I get that, and I put everything together by computing first one more integral, which is that, and then in the end the answer is this. I hope I didn't make any mistakes. I seem to have double checked it as well. So now what are we going to do? We're going to take this answer, the answer we got here, and we're going to use it in the expression we were trying to evaluate, which is this one. So how do we do that? Well, we can just copy paste the expression. But now instead of, well, first of all, I should put back the r here. And instead of the integral from 0 to r of that thing, instead of that, we're going to have, or maybe I would rather keep that there and say that this is equal to the limit stays so far. And now what I want here, once I know the antiderivative, of course, I can get the definite integral by substitution. And so what I want to do is I want to take the antiderivative, which is x squared minus 2x plus 2 times e to the power minus x times 2 plus s divided by minus 2 plus s. And I want to perform there the substitution 0r. So at this point, the limit stays intact, the limit part of the expression, and so putting r and 0. But now the question is where, in the s or in the x? And of course in the x, because we were integrating according to we were integrating by the variable x all the time. And then we're going to get, so putting r in the place of x, we're going to get r squared minus 2r plus 2 times e to the power minus r 2 plus s divided by minus 2 plus s. And then from that we subtract away whatever we get by substituting 0 in the place of x. So that's just going to leave in the denominator, it's going to leave us with one term, and that term is going to be 2 times e to the power, putting 0 in the place of x, we're going to get e to the power 0, which is 1, so we're just going to be left with 2 up there, and then that is divided by minus 2 plus s. And maybe I shouldn't have separated the fraction like that. Let me keep it as one fraction. Rather, I was probably trying to be systematic and write those results of substitution separately, but of course minus 2 plus s does not have any x in it, so it can factor out. So we'll have here minus 2, which is a result of substituting 0 into this expression. Great. At this point, we are done with integrating the definite integral, And what we want now is to move on to finding the value for the infinite integral, which is to take the limit of this expression as r goes to infinity. Okay, so here is another point where we have to pause a little bit and try to wrap our mind around what's going on. Keep in mind that the r came from integral from 0 to r. So the r there is a positive number. So that's an important remark to have at hand. So we know that r is positive. What about s? Well, for s, we haven't decided yet what s should be. We are looking for those s's for which this limit evaluates to finite numbers. So we have some flexibility there to decide to put some restriction on s so as to make sure that the limit will actually exist. Okay, so let us now look at these limits. We can expand, break down the fraction into several of them and compute the limit of each of these. So we'll have limit as r goes to infinity of, what's the first term there? R squared e to the power minus r 2 plus s divided by minus 2 plus s. Then we have plus the limit of minus 2r of e to the power minus r to maybe, actually, I'm not doing it the most clever way. Let me rather, instead of that, do the following. So it is quite evident that in the case when 2 plus s is negative number, we'll have a negative number here, and then it's multiplied by minus 1, and so altogether this will be a positive power of e, and as r becomes bigger and bigger, remember it's the limit as r goes to infinity, as r becomes bigger and bigger, this is going to become bigger and bigger, and eventually the limit of this will be infinity. The denominator doesn't change, it stays this fixed because s does not depend on r. So what about this part here? Again, the limit of this part will be infinity. There's an r squared there, minus 2r as well, but r squared goes to infinity faster than minus 2r goes to negative infinity, so altogether the result will be still infinity. And so in the case when 2 plus s is less than 0, this limit evaluates to infinity, and at least the left hand side part, the right hand side, 2 over minus 2 plus s is not going to affect it because it's a constant number, and the other one is going to infinity. So this is when we say that we do not want this to happen. So we don't want 2 plus s to be less than 0. In other words, we don't want s to be less than minus 2. What we want instead is for s to be bigger than minus 2. And so putting the requirement r is bigger than 0, which we had initially, together with the requirement that s is bigger than minus 2, we can then rewrite that limit as follows. Well, first of all, maybe it is worth remarking that whatever doesn't depend on r, we can just take it out from the limit. So let's do that with minus 2 plus s. And then in here we'll be left with the limit of r going to infinity okay, so now when s is bigger than minus 2, 2 plus s will be bigger than 0, and so here we will have a positive number as well as there, and so we can rewrite the fraction as r squared minus 2r plus 2 over e to the power minus, okay, there's no more minus any longer, so it's e to the power r times 2 plus s. And okay, now we've got a fraction of two things. Individually, of course, the limit of the numerator and the denominator, both infinity when r goes to infinity. But the denominator, because now the power, the exponent is positive, the denominator has goes to the to infinity faster than the denominator, and this can be proved by using L'Hopital's rule. So in the end, by using L'Hopital's rule, we can conclude that, okay, well, first of all, we shouldn't forget the other part of the fraction. So we still have here minus 2 over plus s, so it's going to be 2 over 2 plus s. And so what we get is that by using L'Hopital here several times, we eventually get that this limit is 0, because the denominator going faster to infinity than the denominator causes the limit to be 0. Since the denominator being bigger, the fraction becomes smaller. And so we get that the limit is 2 over 2 plus s, with the assumption that s is bigger than minus 2. Okay, so where are we now? We actually are at the very end, aren't we? So let's go back a bit. We wanted to compute Laplace transform of this function f being x squared times e to the power minus 2x, and we found that that computation reduces to finding the limit of the integral from 0 to r of this thing, and then we got the antiderivative of this thing, so we could get this definite integral. And so all it remained then is to evaluate the limit, and when we evaluated the limit, we got this answer under this restriction of s. So now we can, in the end, we can now write down that L of f, the thing that we were looking for, is equal to 2 over 2 plus s, and that works. So L of f is a function of s, so the value of that function of s at s is equal to that thing, and that works for all s bigger than minus 2. So here we have the domain of the Laplace transform of the given function, and that's it. We reach the end. So you can see here that the main step, well, of course, the first fundamental step is applying the definition of Laplace transform, and then the second step is integration by parts. But then the main step really is the thing that's a bit less trivial and new for us at this point, is carefully choosing values of s so that the limit we're computing actually ends up converging to a finite number, and then using those values of s as the declared domain, and then for that domain we can compute that finite number thanks to the fact that large chunk of the thing we were finding limit for ends up having limit 0. And then this way we arrive to an answer like this. Right. Yeah, so I think this should be clear enough. All the best with your studies.